Alright, hello everyone. So we're going to start in on Chapter 7, which is going to be exclusively talking about solids and liquids. The next chapter, Chapter 8, will be talking about gases. So let's start off by talking about just phase changes in general, and then we'll classify types of solids. Okay? So there are three main phases that matter can be in. And those are solids, liquids, or gas. Right? When you get fancier in your science career, you might talk about plasmas and all that sort of good stuff. But for right now, we're going to keep things simple. 99.9% of all matter can be classified as either a solid, a liquid, or a gas. Okay? So let's talk about the properties of solids, liquids, and gases. So these are illustrations here, and let's sort of go over what exactly we can sort of say about these. Solids are materials that they hold their shape, and they also hold their volume. Right? So if you take for example, like let's say this is a sugar cube or something like that. It doesn't matter where you put that sugar cube in, whether you put it in a glass or a bowl or a plate or whatever it may be, it's going to maintain that same sort of cubic shape, and it's going to have the same volume. Its volume doesn't change. This is different from a liquid. A liquid does hold its volume, right? So if you pour water from one glass to another, it doesn't change the volume of water. Right, so that's why we use measuring cups. We can measure 1 cup of water, that's a particular volume, and then transfer it into our recipe, and it doesn't stop being a cup just because it's been transferred to somewhere new. What it does do is change its shape depending on what vessel it's in. So if we were to pour liquid from 1 cup onto, let's say a plate, it would spread itself out. It would change its shape. Gases, not only do they change their shape, but they will also actually change their volume as well when transferred to a new vessel. Okay? Gases will another way of saying that is that gases will either expand or contract in order to fit whatever vessel they're in. And so what do I mean by that? Let's say that I took this gas here and I put this into a sealed container. All right? So here's my sealed container. And then I took off this lid. What's going to happen? Well, all of these gas molecules that are in this cup right here are going to start to diffuse out, and they're going to keep on kind of spreading themselves out until they're nice and evenly distributed all throughout this box. Right, and so that way, not only did the gas change its shape to fit the container, it also expanded, it changed its volume to fit the container as well. Okay, so these are kind of the simplest explanations of the differences between solids, liquids, and gases. All right, now let's go into type of solids. So 2 different types of solids. There is what's called a crystalline solid. These are the more common ones, and these are the ones that are highly ordered. Okay, so most of the solids that we encountered are fairly highly ordered. The other extreme is an amorphous solid. So this is something that still holds its shape, but the molecules inside, if you were to shrink down and look at the molecules inside, they are not perfectly ordered all the same. Okay, so here's sort of a molecular representation. It turns out that glass is actually like the most famous example of an amorphous solid, which is fairly surprising. You would think that glass, being, kind of the solid that it is, had this highly ordered structure, much like a quartz or a rock, or even, a sugar cube or something like that. But it actually doesn't. And one of the ways that you can illustrate that, or one of the ways that this, you can encounter this over time, is if you ever see a really, really old building, that has glass pane windows. The glass panes aren't exactly flat. They have this kind of like curvature to them. They kind of like reflect the light a little bit weird. And that's because of the slow, very, 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 very slow, kind of like glacially slow pace at which the shapes are changing over time, because glass is an amorphous solid. Most of the solids that we encounter are highly ordered. When solids form, the molecules like to orient themselves in such a way that's most favorable. Okay, so now let's talk about all the different types of solids, like at a molecular level. What's going on there? So we spent a lot of time talking about ionic compounds. Remember, we were able to spot, just given a formula, for example, something like, MgBr2. We were taught how to spot that this is an ionic compound based on where these two, magnesium and bromine, live on the periodic table. So let me just review this real quick. If you're looking at a periodic table and one of your elements live on one side and the other element lives on the other side, you have a nonmetal and a metal, this would be an ionic compound. Okay, so if you have a metal, so that's kind of anything over here, actually not hydrogen, anything over here, and a nonmetal, which was anything over here, those together form an ionic compound. Okay. Ionic compounds are solids at room temperature. Okay, so like sodium chloride is a famous example. That's what's pictured here. That's table salt. That's a solid at room temperature. Ionic compounds form solids at room temperature. They're held together by ionic bonds, right? So if we sort of look in at this highly ordered crystal here, we have these negatively charged chloride ions and these positively charged sodium ions, and it's that favorable opposites attract interaction, what we call an electrostatic interaction, that's holding that crystal together. They're also highly ordered, right? So you can see by this pictorial diagram here, and that has everything to do with these electrostatic forces, right? So positive charges don't want to be next to positive charges. Negative charges don't want to be next to negative charges. So they arrange themselves in such a way such that you always have positive touching negative. And so this leads to these highly ordered solids. They tend to be brittle and crack under force. Okay, so if you were to hit this with a hammer really hard, what happens is you kind of disturb that perfectly ordered network that we were just talking about. And all of a sudden a positive charge is next to a positive charge and a negative charge is next to a negative charge, and it's not really happy, so the whole thing just kind of splits. So despite the fact that they're very strong, they're also brittle. And they also have very high melting points. So those ionic bonds are very strong, right? So we'll talk a little bit about ranking the strengths of these interactions in a bit here. But yes, these ionic bonds are very strong. So these ionic compounds tend to have very high melting points, like 500 degrees Celsius high melting points, incredibly, incredibly high melting points. Molecular solids. So these are solids that are made up of covalent compounds, okay? Similarly to how we had this like trick of looking at the periodic table and knowing whether it was a whether it was an ionic compound, we could do the same thing with our covalent compounds. Remember, if both elements are nonmetals, they live on this side of the periodic table. So for example, the compound that's formed between nitrogen and chlorine would be a covalent compound. Also, hydrogen's a nonmetal. Kind of just lives in the wrong place. So anyways, if you have a covalent compound and it's a solid, it will form what's called a molecular solid. These are held together by what are called dispersion forces. Okay, these are the weakest types of forces Without going too much into it, they just have to do with surface area and molecules liking to be sort of like touching one another. They have, on a more complicated note, they have something to do with minor fluctuations in the electrons, stuff like that. But for our purposes, we're just going to sort of note that these dispersion forces are very weak, and they are what's holding together molecular compounds, molecular solids, just by virtue of these molecules touching one another. If you do have a polar molecule, so last chapter, chapter 6, we would have talked about how you figure out if your covalent compound is polar. If you do have a polar compound, then they're going to be held together not only by these weak dispersion forces, but also by slightly stronger dipole-dipole forces. Okay, so non-polar solids are only held together by dispersion forces. So let's say non-polar held together by those dispersion forces. If you have a polar compound, it's going to be held together by both dispersion forces and dipole-dipole forces. These are still relatively weak bonds, especially like compared to ionic bonds. So molecular solids have relatively low melting points, and they're soft. They're not terribly hard materials. Our diatomic molecules, if you have any sort of a diatomic molecule, for example, chlorine, Cl2, so chlorine gas, these will form solids. These are covalent compounds, and so they will also form molecular solids. They are non-polar molecular covalent compounds, and so they're going to only be held together by dispersion forces. They tend to be gases at room temperature because they just are very, very weakly interacting with one another. So you have to get down to really, really low temperatures before you get them to be solids. Okay, so metals. So this is a new one because we were introduced to ionic compounds when we were learning how to name them. Similarly, we were introduced to covalent compounds when we were learning about how to name them. This is going to be a little new. We're talking about just metallic compounds or metals. So this is if you have something from this side of the periodic table. It's kind of all by itself, right? So for example, if you had silver or copper or iron, a sample of either one of these, when it's all by itself, is considered to be a metallic compound. They are highly ordered three-dimensional arrays of atoms, these metallic crystals. And there's what's called the bonds that hold these together are metallic bonds. So this again is going to be a little new. We've learned about ionic bonds before. We learned about which are all those about those electrostatic forces. We learned about covalent bonds, which are all about sharing electrons. Metallic bonds are what's called this electron sea model. Okay, so a sea of electrons. The idea is that you have, metals don't hold on to their electrons very tightly, right? So we talked about that when we were talking about ionization energy, right? What type of ion does, let's get rid of all these markings. What type of ion does sodium form? Sodium will form an Na plus ion, right? It gets rid of that electron very easily. So metals don't hold on to their electrons very tightly. So what happens when you have these metallic bonds is you have these metal atoms, and the electrons are, again, sort of loosely being held, and they're sort of allowed to flow anywhere throughout these structures. So these metal atoms are sitting in a sea of electrons. These electrons are just kind of freely moving about. All right, so that's what we, for our bonding for metals, what we call metallic bondings is this sea of electron molecules, where you have the positively charged metal ion in a sea of these valence electrons. The free movement of valence electrons is exactly what allows it to conduct electricity. So metals are really good at conducting electricity, meaning that an electron has no problem passing through that structure. They are malleable as opposed to brittle, and so they tend to bend under stress and not break, right? So different from an ionic bond, where as soon as you shift everything a little bit, you've disrupted that perfect network of electrostatic charges. Here with this electron C model, if you sort of put it, you smack this thing with a hammer right here, all you've done is shift these atoms down. They're still floating around in their sea of electrons. So they're malleable and tend to bend and not break under force. The last one are atomic solids that are made up of non-metals. Okay, these are called network solids. So now we have a solid that's only composed of something from this side of the periodic table. So for example, if we had a sample of carbon all by itself, that would form a network solid. Actually, carbon has two different types of network solids that it likes to form. One is the incredibly strong, kind of no stronger material, a diamond. And then it has this slightly weaker one, actually quite a bit weaker one, graphite, which is like pencil lead. The difference is in a diamond, all of those carbon atoms are like connected to one another, whereas in pencil lead, they form these like plates. So that's what makes it quite a bit weaker. So network solids, the atoms in that solid are actually connected by covalent bonds, right? And just to remind everybody, we talked about these molecular solids. They're made up of covalent compounds, but those different covalent compounds are stacked together and only held by dispersion forces, right? So this, for example, this picture right here is ice. Ice is made up of the covalent molecule H2O, but when that solid forms, those different water molecules aren't covalently bound to one another. These different molecules are all interacting through dispersion and dipole-dipole forces. When we're talking about network solids, network atomic solids, we're talking about a single atom, and these atoms are covalently bound to one another. This makes these bonds even stronger than ionic bonds. Very strong. They also have very high melting points for that reason as well. Okay, so just to review our 4 different types of solids: ionic, molecular, atomic, and then network. Ionic are composed of, ionic compounds, right? And remember, we can spot an ionic compound based on where those elements live on the periodic table. Those are held together by dispersion forces, although those are really, really weak, so they don't play a dominant role here. The important part is that they're held together through ionic bonding. Okay, so anything that's touching is really held together by dispersion forces, but that's not the one to focus on. The big one that's going to have all the effects on the properties of these solids is the ionic bonding. When you have a covalent compound, which again we should be able to spot based on where it lives on the periodic table. First, you have to decide whether your covalent compound is nonpolar or polar. Nonpolar molecules will only be held together by dispersion forces. If your molecule's polar, it will be held together by both dispersion forces and dipole-dipole forces. Dipole-dipole forces are stronger. And actually now this is a little something new we're going to throw in here. If your polar molecule contains one of these 3 polar bonds, NH, OH, or FH, these are special kind of dipole-dipole forces that are especially strong, called hydrogen bonding. So if you have a polar molecule that has one of those 3 types of bonds in it, it will be held together by dispersion forces, the even stronger dipole-dipole forces, and the even stronger hydrogen bonding forces. If you have a metallic solid that's, so an atomic solid meaning single atom, and that single atom is a metal, it will be held, get a different color, it will be a metallic solid held together by, again, those weak dispersion forces, but importantly, that metallic bonding. Remember, we called this that sea of electrons model of bonding. And if we have a network solid, which is also made up of single atoms, but they're nonmetals, these are covalently bound solids. So it's called a network solid, which means that the atoms are all covalently bound to one another. Okay, so this is a nifty little flow chart that your book gives you that can help you sort of decide what type of forces are holding together a particular solid. Okay, so let's get some practice using this here. We're going to use it for iron, calcium bromide, iodine, and sulfur dichloride. So let's just go through each one of these. So iron. Is this substance an element or a compound? I just got the one here, so that's iron. Iron is an element. Is it atomic or molecular? Okay, this would be an atomic ion here. An atomic element here. There's just one of them. Okay, we'll see a different example where that's not the case. And is this a metal or a non-metal? Well, if I look on the periodic table, I can see that iron lives right here in the transition metal block. So iron is indeed a metal. So it will form an atomic crystalline solid held together by those metallic bonds. Okay. Let's actually jump to do this iodine example here, because this is going to be kind of the counter. Okay, so I2, is it an element or a compound? Well, there's only iodine involved, so this would be an element. However, it's not an atomic element, it's a molecular. It's a molecule, right? So these two iodines are bound together in a molecule, so this would be a molecular compound. That means that it's held together only by dispersion forces. So molecular crystalline solid held together only by dispersion forces. So iodines are held together by quite weak forces compared to iron. All right, calcium bromide. Is this a element or a compound? Well, we got two different elements, so it's definitely a compound. Is it ionic or molecular? You guys take a look at the periodic table here and see if you can't tell me whether calcium bromide is ionic or molecular, meaning covalent. So calcium's over here, bromine's over here. Since they're on opposite sides of the periodic table, this would be ionic. So that means that calcium bromide is a crystalline solid held together by ionic bonding. And then lastly, sulfur dichloride, SCl2. This is again a compound. We have both sulfur and chlorine. Looking at the periodic table, would you expect this to be an ionic compound or a covalent compound? Sulfur and chlorine, they're both on that non-metal side of the periodic table. So this would be a covalent or a molecular compound. Does the molecule contain, is the molecule polar? All right, so this would be the tough part where we actually would have to go through and draw the Lewis structure in order to determine whether or not this molecule is polar. I'll give it to you here. Okay, from that Lewis structure, can you guys determine whether this is polar or non-polar? Remember, if there's lone pairs on the central atom, then it is indeed polar. So we're down here. Gosh, my handwriting. Now, does the molecule contain either a fluorine, hydrogen, oxygen, hydrogen, or nitrogen, hydrogen bond? In this case, that would be a no. So sulfur dichloride is a molecular crystal held together by dispersion forces and dipole-dipole forces. Okay, so this flowchart's a handy way of sort of being able to figure out, given the compound, what are the forces that are holding it together.